Next, we discuss how to model an optical waveguide. The objectives are to model the waveguide in order to understand the propagation speed. We already know that the index of refraction is not a constant due to material dispersion. In this section, we will learn about waveguide dispersion. These two effects are additive. The objective is to calculate the propagation constants, which we describe using the effective and group indices for the waveguide. The effective index is the same concept as the index of refraction, except that it describes the phase velocity of light in a waveguide rather than in a homogeneous medium. We want to know their wavelength dependence as well as their geometry dependence. As a designer, you have some ability to control the waveguide geometry, namely the width. This will impact the propagation constants. We begin our discussion by analyzing the SOI wafer. By itself, the wafer forms what is known as a slab waveguide. The light is guided in a plane. We consider propagation from left to right in this diagram along the x-axis. We will calculate the one-dimensional mode profile along the z-axis, which we define here as perpendicular to the wafer or wafer normal. This is the vertical direction in this diagram. Most work in silicon photonics has been focused on the fundamental mode of the waveguide, which, as we will see, is quasi-TE polarized. Thus, we begin by looking at the TE polarization of the slab. This means that the light's electric field is transverse or parallel to the wafer. The mathematical details of solving Maxwell's equations for optical waveguides can be found in many optics textbooks. Here we provide the MATLAB code which implements the solution as described in Yariv's textbook. This code finds the waveguide mode parameters and returns the effective index of the slab waveguide. We can plot the results and see the field profile as a function of the position in the wafer in the thickness, or wafer normal direction, which we label here as height. We see that the light is primarily in the silicon, but some of the light is also present in the cladding. In this example, we use the cladding of air instead of silicon dioxide. With such calculations, it is useful to ask an important question. What is the single mode condition for the slab? This question is answered by two sub-questions. The first is what is the maximum thickness for the silicon before it supports more than one mode? The second is what is the minimum thickness of the silicon before it does not support a mode at all? We can answer these questions by performing parameter sweeps, namely by varying the thickness of the silicon. We wish to study the effective index of the slab versus the slab thickness. These are simulations for a wavelength at 1550 nanometers. The plot shows the effective index as well as the polarization, TE versus TM, for different modes supported by the waveguide. Note that for a 1D waveguide structure, the mode is either a pure TE or a pure TM mode. This is in contrast to 2D waveguides, as we will see later, where pure TE or TM modes do not exist. The dotted line is the index of refraction of the oxide. Modes with an index below this value are not guided and are numerical artifacts. For slab thicknesses below 240 nanometers, we can see that there is a single solution for each polarization, namely TE and TM. This is indicated by the vertical line, which shows the onset of guiding for the third mode, which is TE polarized. This explains why 220 nanometers is commonly chosen for silicon on insulator substrates for a wavelength of 1550 nanometers. These graphs are useful in designing waveguides with different thicknesses, wavelengths, and polarization. Silicon photonic circuits are typically designed to operate in a single mode, either TE or TM polarized.